All right, in the second part of the Atom Study Guide podcast, we're going to finish up with transmutation equations and half-life. All right, so first let's talk about what is fission. Fission is when you take a large molecule, or a large atom rather, and you break it into smaller atoms. So it breaks down into something smaller. Okay, so big nuclei breaking into smaller ones. Okay, so radioactive decay is an example of fission. All right, fusion is the opposite. It's taking small nuclei, combining them, and we get one big nuclei. Okay? When a nucleus becomes unstable, it undergoes radioactive decay or fission in an effort to achieve a more stable nucleus. So why was that nucleus that underwent decay in the first place unstable? Well, this has got all to do with the protons and neutrons. So it's got the wrong proton to neutron ratio. All right, now that we're going to look at some examples of some nuclear equations. All right, to solve nuclear equations, remember that you pretend that the arrow is like an equal sign, and you look at just the top numbers and just the bottom numbers separately. So we have 238 equals 234 plus x. So the top's going to be 4 there. And then 92 equals 90 plus x. So 2 here, and we know that alpha decay has that symbol. All right, same thing here. So 234 equals 234 plus x, so the top 0. And 90 equals 91 plus x. So 91 minus 1, so that's our x value, is equal to 90. And that is a beta particle. So that's beta decay. All right, now 234 equals x plus 4. So 234 equals x plus 4, so 230. And then 91 equals x plus 2, so 89. All right, and when you look on the periodic table for the atomic number 89, you see that is element actinium, or AC. All right, the next one you have Rn, so 220 is equal to x plus 4, so 216. And 86 is equal to x plus 2, so 84. And then element 84 is PO, which is polonium. All right, element 84, polonium. So we have 216 equals x plus 0, so the top remains the same. It's just 216. And then 84 is equal to x minus 1. So 85 minus 1 will give us 84, and element 85 is AT. And then we have 14 equals 14 plus 0, and then 6 equals 7 minus 1, so that's a beta decay. And then this very last one down here, it kind of got cut off. It's 210 Bi. And Bi is 83, and that is decaying by beta decay. So we know beta decay is 0, -1, B, or you could have put an E, and that's going to turn into, the top's going to still be 210, and then the bottom is going to be 84 minus 1 is 83, and element 84 is again polonium. All right. This is an extra credit type problem. It's a little more advanced. So you know that you have element 247, BK, and BK's atomic number is 97, so that's the bottom number. And it decays by some number of alphas and then some number of betas, and becomes lead 207. All right, and lead is element 82. So we want to find how many alphas first based on the top number, because beta doesn't affect the top number, only alpha does. So we have 247 equals x. We're going to call however many alphas we have x. So x times 4, and then 0 here, so we don't have to worry about that, plus 207. So subtract 207 on both sides. It gives you 40 is equal to 4x. So x is 10. So you have 10 alphas. Now you can find beta rather easily by setting the bottom number. So 97 equals 10 times 2 is 20. And then we're going to call the number of betas y. So we have y times -1, which is -y, plus 82. All right, so we really have 102 minus y, and then subtract 102, you get -5 is equal to -y. So 5 is how many betas you have. So that's how you would approach that sort of problem. Here you have a graph of uranium-238 decay, and we know that this uranium only goes on alpha and beta decay. Wants us to tell us the first 4 decay particles during the chain. So here's the first one, and we see that the first thing that happens is that the mass number and atomic number changes. So that's got to be an alpha. All right, then we have a change that only the atomic number changes, and again, so we have 2 betas and then another alpha. So you've got alpha, beta, beta, alpha. So you need to look and see if the atomic number is changing or both of them are changing. All right, half-life. Now when you're tackling half-life, you always want to make yourself a chart of time and your sample. Remember that time always starts at 0. So it says you have 5 grams of iodine left after 40.35 days. What was the original sample of the iodine if the half-life's 8.07 days? So every time there's a half-life, you add 8.07. So we got 8.07 plus 0. Then 8.07 plus 8.07 gives us 16.14. Plus another 8.07 gives us 24. I think I wrote an 8 there, 81. And then that plus 8.07 gives us another, this is a 20, y'all, 21, there we go. All right, gives us another, so that's 32.28. And then another 8.07 gives us 40.35. Now we know that after that much time, we have 5 grams left. Now every time a half-life goes by, we lose half our sample. So if we're going backwards, we'd be doubling our sample every time. So we go to 10, to 20, to 40, to 80, and finally the original sample at 160 grams. Okay? All right, let's look at the second problem, and then let's apply the same technique of the time and sample chart. All right, so it says that our half-life is 8.1 days, so we know that the first half-life we're going to 8.1 days. How long? So we want to figure out the time for only 25 grams of a 100-gram sample to be left. So you start with 100 grams, and you have your first 8.1 days, and it cuts in half. And then after another 8.1 days, it cuts in half again. Oh, you're already at 25. So 16.2 days. Okay? All right. Here's another 2 half-life problems. Again, we're going to set up our time and sample charts. And we have time starting at 0. And it says that we have a 250-gram sample left. How much is left? So that's what we start with. We're starting with 250. Is left after 388.8 days. And our half-life is 97.2 days. So we got 0 plus 97.2 is 97.2. And then 97.2 plus 97.2 is 194.4. 194.2 plus 97.2 is 291.6. And 291.6 plus 97.2 is 388.8. And we need to figure out how much we have. So every time a half-life went, we lost half our sample. So we get 125 there. And then that bumps us down again, cut in half, to 62.5. And then it cuts in half again, 31.25, and then again at 15.625 grams. So that's how much we have left after all of those half-lives. All right, the last question wants to know the half-life of the TC99 element. If a 500-gram sample decays to 62.5 grams in 639,000 years. So I'm going to make it up here because it'll be easier for us to see. Again, time's always at 0. And we started with 500 grams. Now we know that our sample cuts in half every time, and we want to get to 62.5 grams. So if we keep cutting in half, we see we reach 62.5 grams after not very long. Now we know that that amount of time that has lapsed has been that many years. So we've had 1 half-life, 2 half-lives, and then this would represent the 3rd half-life right here. Okay, so basically take this number, divide it by 3, and that'll give you the half-lives, which are, let's see, 639,000 divided by 3 gives us 213,000 years. And that's all what you got to do there.